Yes, good.
Okay, so I will talk to you about air management system or environment control systems. I will talk about 8821, that's air conditioning, 8826, that is protection, but I will talk to you about only smoke containment and detection and containment. And then I will talk about 8836, that is bleed, and 8847, that is inertization, fuel tank inertization. Okay. My name is Fabio Stabile de Oliveira, and I am a mechanical engineer. I have 18 years of experience in aeronautics with development of environment control systems. In fact, development, simulation, and certification. I was working together with Clarissa and Rafaela and Franco and Felipe in Mitsubishi, but since last December, I have retired from there. And I have experience in other industries like infrastructure and biomedics, and I also was a university professor some time ago. But it's just for fun. I like thermodynamics, machine component design, heat transfer, material strength, design of aircraft structures, mechanical vibration, and manufacturing process. Well, I will start to describing the ECS by telling you about the problem in which aircraft needs to deal with, that is the atmosphere. As you know, the atmosphere in which aircraft flies has extremes of temperature, pressure. There are other critical things involving in operation like cosmic radiation and sunlight UV. As higher as you go in the atmosphere, you have more UV content. And also, sometimes the aircraft flies in an environment with high content of toxic compounds, for example, like ozone. And the aircraft sometimes generates toxic compounds in some failure conditions or even in normal operation. And as you know, we are not tolerant to all these extremes of atmosphere and all these agents. For example, here is some limitations. It's temperature, lower humidity. When you have lower humidity, your airways tissues can be damaged by that, became more susceptible to disease. And also excessive humidity can affect our heat rejection mechanism. We have a limited capability to exposition to lower pressures. If we start breathing in lower partial pressure, we cannot absorb oxygen, depending on the partial pressure of the oxygen, and we can die because we will have a risk of hypoxia. Our tissues are not too much tolerant to cosmic radiation. As higher as we go, more cosmic radiation content we will have. The skin cells can be damaged by UV content of sun radiation. We are very sensitive to excessive noise. We are not tolerant to big accelerations, and we cannot breathe toxic gases like ozone, for example, like CO, CO2, some acids, some chemical compounds that are released in case or smoke. And currently, we have this new issue. In the last 20 years, we have some infection diseases that are affecting the aircraft operation. In the beginning of 2010s, we have SARS, we have MERS, and we had SARS, we had MERS, and now we have COVID. And despite all these things that ECS needs to deal with, we have other concerns. For example, we need to develop an aircraft that are comfortable in terms of temperature, in terms of noise. And we cannot make aircrafts with extremes of temperature, or otherwise people will complain, will not like to fly. Well, and ECS shall not deal with human beings, shall deal also with the delicate electronic equipment. Electronic equipment are not susceptible to extremes of temperature, and in case of failure, they release toxic gases. And you know, in the recent years, the electronic content of aircraft are increasing. So aircraft is becoming more intelligent, and we are having more and more computers for controlling aerodynamic surfaces. And additionally, we are having more electronics inside the cabin to, like, for example, the in-flight entertainment equipment. And not only all the electronics that we are putting inside the aircraft, but in the future we will have more electronics, because people now are discussing more and more about the more electrical aircraft concepts. So the manufacturers of aerospace systems are changing from mechanical conventional systems for actuation and ECS, and they are migrating to more electric architectures. So instead of having mechanical power, hydraulic power, bleed power, we will have electrical power to move the aircraft systems. So I will start with 8836, that's the Phenatic system. So for ECS system, bleed is the primary source of energy for these systems. So what is bleed? Bleed is compressed air extracted from engine and ducted to the systems that requires power to be moved. So in the engine, normally we have two ports for extraction of bleed. One port is a low pressure port, and the other port is high pressure port. In fact, we have two positions in the compression. One in a lower compression, lower pressure compressor port in the compressor of the engine, and the other is in high pressure port. For example, some engines you extract the bleed from 9th port, and others for low pressure, and in 14th port for high pressure. Let's say that we have 16 stage of compressor. We can use combinations of this stage to have a low pressure port or a high pressure port. After the extraction of bleed from engine. You have the precooler to reduce temperature to 200 degrees to keep the bleed below ignition condition for fuel. So for jet A, 200 degrees is considered the temperature in which we can prevent from ignition during distribution of the bleed. And then we use the bleed in many systems in the aircraft. For example, in the air conditioning pack, in inert gas system, to pressurize the potable water system, or as energy to provide anti-ice function for the wings, and sometimes for other components in the aircraft, for example, the windshield, or engine inlets, for example. But there are other places when we need compressed air. For example, as wiper, there are some aircrafts that use pneumatics to wipe out water from windshield. We can use as a defog for windows. I don't know if you know, but for example, the PEX windows of Concorde was defogged by bleed. Okay, it's one example of how we can use bleed for defog windows. There's a 2 layers windows, and then you insufflate bleed in between the layers of glass. And we can also use in PEX doors seals. So to make a good seal in the PEX door, you can pressurize the seal, the rubber seal. And also you can pressurize fuel tanks. The Perimatic system is provided with some features to avoid hazard. For example, if you have a leakage of compressed air at 200 degrees C, it will not be good condition for the airframe and for critical systems. So we have leak detection. And additionally, because the ducts operate at 200 degrees C, we have thermal insulation in the surface to protect the surrounding systems and to preserve the thermal energy that is transported inside the ducting. System is monitored for failure. In case of failure, let's say that we have a leakage, this leakage system will detect the leakage and shut down the system. And the system is integrated with other systems in the aircraft. For example, it is integrated in fire prevention and with aircraft systems, with anti-ice systems, and with propulsion systems. For example, in case of Fedel request all the engine power to perform a takeoff, a takeoff, for example, the Fedel will ask the ECS to shut down the bleed from compressor because engine needs to prioritize the thrust for takeoff. Another example is when we apply the thrust reverser during landing. Some aircraft will not have enough bypass flow to cool down the bleed because the thrust reversers will launch the bypass flow to break the aircraft. In this condition, the ECS controller will shut down the bleed to preserve the temperature to an acceptable level. So here there is a a little sketch showing for you where the ducting of the pneumatic systems is routing across the aircraft. So this is the bleed lines connecting the sources that are the engine and APU. You see, can you see my mouse?
Yes, we can see it.
Oh, thank you. So you have the engine here, so you have a duct that crosses the pylon, joined with this duct on leading edge of the wing. One side here, this side here goes to the anti-ice system. The other side goes to the aircraft systems. The procurer normally is installed in this position here over the engine. So in this other view here, you can see some systems, some consumers that are fed by the bleed ducting. And this branch here connects with APU. APU is the primary source of bleed for ground operation. Sometimes it works beyond ground during takeoff, for example, to a certain altitude. Here you have a picture of engine and of APU. The bleed ports here in engine is not easy to see, but here in this picture of APU, you can see the bleed port here. You can see here is the inlet, air inlet of APU. Here is the compressor case. You see that is reinforced. You can see the reinforcements here. And here is the position of combustion chamber. And this annular duct here connects to this red cap. That would be the position of the bleed ducting. After here, you have the line that I have shown in the previous pictures. Normally, APU is installed in the tail of the aircraft, and here normally is the exhaust. Sometimes the exhaust is in the bottom portion of the tail cone, but the configuration is very diverse. There are many layouts of APU installation. But traditional, it is installed in the tail cone. Here you can see an engine. Here you can see two ports of extraction in the compressor case. This is the front portion of the compressor. You can see here the mechanism for the guide vanes. And this mechanism regulates the attack angle of the guide vanes. And after compressor, you have a high pressure port extractions here. They are capped in this case. But normally, if you look for on engine, you find the bleed manifold going outside engine in this position. Here, the bleed duct is not installed, and these extraction ports are capped. Another thing that you can see in this picture is the air start turbine. So the air start turbine is driven by bleed. So you see here, this is the I think this is the air start turbine. The air start turbine, I don't have sure, but it seems that is the air start turbine. The air start turbine is the mean in which the engine is started up. So here is the gear case. There is an axis that connected to the axis of, I don't know if it's N1, probably is N2. And then there is a clutch here that engage the air start to the gear case. And the primary source of energy would be a turbine that will run the rotor of the engine until it's capable to start up itself. So in the big engines, it's more common. We have pneumatic startup. Just a few little engines, and for little airplanes that has electric motor to start up the engine. The bigger ones used to be started up with pneumatic source. And which is the source for starting up the engine? It can be the APU, but you can also use a pneumatic startup ground cart. So basically, EPU generates here compressed air. The compressed air is ducted to the engine, and through the engagement of air starter turbine, the engine will be started up. APU also provides electrical power for the aircraft. So here you can see a generator connected to this gear case that will be able to feed the electronic distribution system of the aircraft on ground. And you can also use a ground power unit, but when you don't have ground power unit in the airport, you can use the APU generator to provide energy, electrical energy for the aircraft. Okay. This is not a common big airplane APU. This is a little airplane APU, but for the bigger airplanes, APUs are very similar to this one. So here we have schematics of the Binomatic system. So as I told you, the extraction is in the compressor of the engine. So we have two extraction ports. This is a typical diagram. Not all the airplanes has the same diagram, the same layout for the system. But in this slide, you see a typical diagram. The majority of airplanes are similar to this diagram, but there are airplanes that have different layout and different technologies employed in the bleed system. So this is the extraction port, the low pressure. This is the high pressure port. And normally you have a check valve in low pressure and shut-off valve in high pressure port. If shut-off valve is closed, the low pressure port will provide bleed through this check valve. And downstream, you have a pressure regulating valve. Some aircraft has only shut-off valves in these two valves here. But for example, in this diagram, we have a pressure regulating valve. This pressure regulating valve can be controlled by a digital controller that will read the pressure in the manifold and controls the set points. And inside the fire zone, you have a pre-cooler to reduce the temperature of the bleed by using the bypass flow of the engine. So here you have the funnel valve. The funnel valve is a modulating valve that has its modulation controlled by the temperature of the bleed. So the bleed systems has several set points, sometimes one set point for anti-ice operation, or different set points in case of failure. For example, let's say that we have a failure of one of the systems. Let's say that the right side system has a failure and the bleed valve here is shut down. So to provide enough energy for operation of all aircraft systems, we may have to increase the temperature set points. So we will modulate the funnel valve and PRSOV valve to reach different level of pressure and temperature to provide enough energy for all the systems. And here I put that the HP, the high pressure valve, it's a pressure regulating valve, but normally this valve is only a shutdown valve. However, to avoid transients, sometimes aircraft needs to control the time for opening and closing this valve. So this valve, despite this valve required to be only a shutdown valve, sometimes this valve is required to have an adequate time to close or to open. So it should be controlled also. Okay. And here you have other systems. For example, this is the engine starter valve. And as I told you previously, this duct is connected to the air start turbine of the engine that provides power to start up the engine. This valve is also a regulating valve. And it's commanded by a Fedel with the signal from AMS controller. And here we have another valve that can be also only a shut-off valve or a pressure regulating valve. That is the nacelle lip anti-ice. And this branch of the engine anti-ice warms up the inlet of the engine and use bleed to do this function. And here we may have normally a shut-off valve, but sometimes it's a pressure regulating valve. And well, and here, after this point here, normally the firewall is positioned in this point. After this point, you have the distribution for aircraft systems. So here you can see, for example, the wing anti-ice system. Here you have a regulating valve in the inlet of wing anti-ice. This is a system that warms up the leading edge of the wing to avoid ice deposition during flight. Ice can impinge on the leading edge of the wing, and wing can lost its aerodynamic capability. So for this reason, to avoid hazard, for example, like a stall condition, it's important to de-ice the wings and avoid ice to build up in the leading edge. Here we have other systems, for example, the air conditioning machines that provides fresh air for cabin. And we have two air conditioning machines, one for left hand, the other for right hand normally. This is the inert gas system that requires bleed air to provide inert gas to provide inertization function for the fuel tanks. To avoid ignition inside the fuel tanks, you need to provide inert gas to avoid we have a flammable atmosphere inside fuel tanks. So we reduce the oxygen content using bleed. So these systems provide is fed with bleed, and then the system reduces the content of oxygen from bleed, and then inflate inert gas inside fuel tank to avoid the flammable condition inside fuel tank. There are other functions for the bleed system. For example, we can use ground card to perform startup of the engines. So there is a ground connection with a check valve. And also, if we don't have bleed from engines on ground, or even in flight, if you have failure of the bleed system, we can fit the system with APU. So you will have an APU shut-off valve. Sometimes this APU valve is also a regulating valve. And downstream you have a check valve to avoid leakage case this failure or APU fail, or we have any rupture in ducting here, we have a check valve here. Downstream the air conditioning machine, you can connect also a ground card to feed the aircraft in the lower pressure ducting of the air conditioning system to provide air conditioning for the aircraft when you don't have any bleed source on ground. So this is the basic schematics of the bleed system. Here is a schematics of the pressure and temperature control. So as I told you, the temperature control function is done by the funnel valve and precooler. And the pressure control function is performed by the pressure regulating shut-off valve here. So the AMS controller reads the pressure and temperature in manifold and provide commands for these valves here. By modulating the funnel valve, you can control temperature, and by modulating the pressure regulating valve, you can control the pressure. Okay. Here you have another, for example, I put the Fedel, the full authority digital engine computer is the computer that controls the engine. The computer receives the input from aircraft and from engine, process the inputs and send signals to the AMS controller. So let's say that the pilot has configured for a given takeoff. The pilot would, the runway is short. The pilot is afraid of not being able to perform the takeoff. So the pilot goes in the cockpit and configure the aircraft to perform a high power takeoff, high performance takeoff. For example, let's say that it's in that particular aircraft, the code is takeoff 1, for example. So after pilot has configured the aircraft to perform takeoff 1, when the pilot requests power in the thrust lever to full power, for example, the Fedel will send a digital signal to the AMS controller, say something like, hey AMS, please shut down the bleed because I will need to prioritize thrust. So AMS controller will shut down these valves here, and we have all the compressor power to the combustion chamber to move the air, to prioritize the thrust in that particular condition. Okay. So here is some samples of Pneumatic system components. This is a pressure regulating shut-off valve manufactured by Liebherr. Basically, it's a butterfly valve with some special metals. Sometimes you manufacture these valves with titanium, with Inconel, or stainless steel. And here you have a piston that moves the butterfly, and piston is commanded by a torque motor that normally is installed in the aircraft. Normally is installed in the valve body. So the torque motor will receive the analogic signal from the AMS controller, and with this analog signal, the piston will be controlled and will provide modulation for the butterfly here. Here you have a typical bleed check valve. It's a two flapper check valves, as you can see. And here there are some samples of percoolers. So these percoolers are manufactured by Honeywell. I think 10 to 15 years ago, Honeywell has bought one company in Europe named Secan, because these percoolers here were manufactured by Secan. This 777 is a 90s aircraft. The aircraft manufactured and development in the 90s. So probably this percooler was not manufactured by Honeywell, but by Secan, that is a French company. So basically, percooler is a thin plate compact heat exchanger. And here you can see this is the bypass side of the percooler. So probably here comes the ducting from the bypass of the engine with cool air. And here is connected the bleed from the compressor. So the bigger hydraulic passage through a percooler normally is the bypass. So here is the bypass side, and here is the bleed side. Here is the bypass side. Probably this is the outlet. And here is the bleed side. Here is the bypass side, bleed side. Here is the bypass side, here is the bleed side. These percoolers used to be manufactured with heat-resistant alloys. For example, here is Inconel. And another issue with percoolers is the stratification of bleed temperature. If you have a temperature sensor here in the outlet of percooler, because of the nature of this component to have distributed temperature parameters inside, probably you have stratification in the outlet. And in this picture here, it's clearly show a mixer. So here you have a fins that the intent of this fins is to mix the stratification that's generated inside the heat exchanger, and to mix the streams here to be easy to control the temperature, because you have a temperature sensor here that will control the funnel valve. And if you have a wrong reading of temperature, you will not be able to control the temperature. So this is another hydraulic element that contributes to avoid stratification in the outlet. Well, the next system that I will talk about is the air conditioning and pressurization system, the 8821. Okay. The air conditioning of a large civil transport is normally performed by an air cycle machine. And it's responsible for temperature control, humidity control, and inflow for pressurization. The machine provides fresh air for the cabin and cockpit at a controlled temperature. And the pressurization is controlled by an outflow valve that controls the outflow of the aircraft. We have a pressurization controller that modulates this valve to reach a given pressure set point inside cabin. So here you have a schematics of a PEC. What is exactly a PEC? PEC is an acronym that stands for Pressurization and Air Conditioning Kit. So it's a kit that provides air conditioning and flow for pressurization. Normally, PEC is installed in the belly fairing of the aircraft. Here you can see a NACA inlet, and here there is a grid outlet. So here is the schematic of PEC. So here is the bleed inlet. So bleed is provided here. And here you have the NACA inlet, and here you have this grid outlet. So it's basically a flow machine that has a compressor and a turbine. So bleed is provided to this machine, pass through a ram air heat exchanger, a primary ram air heat exchanger, goes to the compressor compresses the air to a secondary heat exchanger that use ram air to cool down, and then the bleed is expanded to a turbine and goes to the cabin. Here, this is the set point of temperature of cabin. Normally, the PEC delivers the air something between 0 degrees C and 5-8 degrees C. So the temperature here is very lower compared to the cabin set point. But there is a bypass that provides hot bleed to modulate the temperature in the outlet. So this is basically how a PEC works. Here you have a schematics of the air conditioning system. So you can see here is the PEC and here is the bypass. So both PECs are connected to a mixed manifold. And then you can ask yourselves, how the humidity is controlled? Well, humidity normally is controlled by recirculation. Because we have many people inside cabin release humidity by breathing the air. So we collect the air through the recirculation system and mixed breathed air, air that has been breathed by people and is with a lot of humidity, and mix this air with fresh air that comes from PEC, and distribute this air through cockpit and cabin. The temperature is modulated here by this bypass. So you have these stream valves here that are modulated by the AMS controller and to reach the cabin temperature set points. So here you have in the cabin and cockpit, you have temperature sensors that are connected to the AMS controller. And in cockpit, the pilot will regulate the temperature in these knobs here in the air conditioning Pneumatic panel. So here is for example, the temperature control for cockpit. Here is positioned in the full cold condition, but it can be everywhere here. And in the aircraft panels, you have the digital reading of temperature sensors and additionally the set points. So the set points and temperature reading for each environment is shown in the multifunctional displays of the cockpit. And here you have the outflow valve. So you have here the inflow and you have here the outflow. And the outflow valve controls the pressurization inside cabin that is controlled by a digital controller. And here you have the pressurization panel. The pressurization normally is automatic. So here the mode is automatic, but you can have manual mode. And then you configure you control in the manual mode, you control the pressurization by this knob here. So in the multifunctional display of the aircraft, you can increase or reduce the cabin pressure by moving this knob here. Moving this knob here. Okay. This is an installation of HEPA filter. in recent days, since the last disease that has occurred in the aviation, like SARS and MERS, since there, and now even more with COVID, the aircrafts are required to be operated with HEPA filters. These filters provide a good protection for bacteria and for virus. And you can see here in this link here, you have a good article explaining how EASA is dealing with this subject. Currently, HEPA filter is very efficient to filtering viruses from cabin air. And EASA is advising, I think all the aviation are prioritizing the good utilization of these filter systems to avoid contamination inside cabin. So the next system that I will talk about is one system that incorporates in the air conditioning, that is the avionics cooling system. So in the airplane, not only the people are important, but also the electronics. So the avionics cooling system uses the return air from air conditioning to cool down the electronics. So normally the electronics are organized in electronic bays, and the bay shall be designed to meet these requirements here. Normally, they shall meet the environment requirements of the electronic boxes, the integrity of the aircraft, the smoke detection and containment, in this case, contamination with hazardous amounts of toxic gas of occupied zones are likely to occur in case of failure. So electronic cooling systems shall avoid this. The bay are segregated by power buses normally. Well, several cooling architectures of cooling can be present, but the most common in large aircraft transportation use, for example, for non-pressurized zone uses Bremmer, or natural convection for pressurized zones, or forced convection using as a heat load the air conditioning system. For example, for conditions where we don't have PEC heat load, in case of PEC's doors are open for ground operation, for example, normally we install fans to perform cooling for ground operation. So air conditioning works properly only when the PEC's door is open. For the conditions, when PEC's doors are closed, the air conditioning works properly, ventilating all the aircraft. When the PEC's door is opened on ground, for example, you will need a cooling fan to perform the ventilation inside the aircraft. So here is the general schematics of how avionics cooling works in the large commercial aircraft. As I told you, we use the return air from cabin. So after people breathing, the air goes to the return area of air conditioning, where the electronics compartment are installed. Okay. Sometimes these electronic compartments receive the return air from air conditioning to cool down the electronics. And the base normally has an exhaust fan and a temperature sensor to check if the temperature is within the limits of the electronics. So people breathe air at no higher temperature, at a temperature not higher than 29 degrees C. but the electronics can work well up to 70 degrees C. So the ACS controller needs to monitor if the temperature in the base are below 70 degrees C. So in case we have an obstruction of the inlet of the bay, the ACS controller will monitor its temperature. If the temperature exceeds the acceptable temperature for the electronics, it will indicate, it will put a message for the pilot, indicate that we have a problem in the system, and pilot needs to take an action, okay? And the flow normally is driven by a fan that provides exhaust for the base. Inside the base, you have several types of electronics. There are electronics that are natural, receives only natural convection. There are electronics that has units that has their own ventilation fans. And there are electronics that has fins for heat dissipation. In all the cases, we will have some airflow to remove the heat load from these electronics, okay? And the outlet will be driven by a cooling fan. The outlet flow can be can be launched in the outflow valve or can be launched in the recirculation bay. Currently, for comfort purposes, it's not a good thing to recirculate electronics cooling air, because sometimes electronic cooling air has some volatiles released by the electronics equipment that cause not so good smell in cabin. So for comfort purposes, the good way of deal with the system, with the outlet air, is to launch directly into outflow valve and avoid recirculate this air. Otherwise, you have electronics smell inside cabin, and this smell is not good for the occupants. And sometimes you have an outboard valve. This outboard valve is used for cases when one of these units releases smoke. The other system that I will talk about for you is the Inertia System ATA47. So this system, as I told you in the schematics of the pneumatics, is responsible to provide inert gas to ventilate the fuel tank. So normally this system provides air with oxygen content lower than 3%. That is very below the flammability limit of the fuel tank. So here is basically how this inertization system works. It receives bleed from the pneumatic system, and the bleed passes through these plastic fibers. These plastic fibers, the oxygen can permeate outboard here through this wall. So when these plastic fibers are at a given temperature, they will be more permeable to the oxygen, and the oxygen will be vented out to the outboard. And after passing through these fibers in this other portion of the air separation module, you have a flow that is more nitrogen than oxygen, approximately 3% oxygen. So here is a basic schematic of our inert gas system. Here the systems provide, the bleed system provides bleed for the inert gas system. We have an ozone converter in the inlet. We have a shut-off valve. We have a temperature control valve. In case of being above the set point, this valve modulates the flow. So the flow passes through a heat exchanger in the ram air circuit of the packing let. And here you have a temperature reading to modulate this valve. And then after this, the bleed goes inside to an air separation module. And in the outlet, you have the oxygen measurement device, and you have a flow sensor that modulates this valve here. That's the flow control valve. And after all these manifolds of sensors and valves, the flow goes to the fuel tank to ventilate the fuel tank. Okay. The other system that I will talk about you is the smoke detection and containment system. So this system is responsible to detect smoke in case of failure in the base. So let's say that you have an electronic box there that has failed and starts to release smoke. This smoke, we don't know if it's toxic or not, but this smoke may have good content of contaminants that can cause hazard for the occupants. So in this condition, we need to avoid the contamination of occupied zones. People cannot breathe these toxic gases, and we need to detect that this failure has occurred, because pilot needs to take action to isolate the bay, to shut down the electronics that's causing the smoke. And if pilot is not able to shut down the smoke, pilot needs to land the aircraft and evacuate the aircraft. So this system is responsible for doing all of this, okay? So system comprises the smoke detector that detect the smoke, and some logics that, for example, shut down the recirculation fan. Because if you detect smoke inside the aircraft, you can stop the recirculation. Okay, people will start to feel their throat, that their throats are becoming dry, but well, it's a short exposition. It will not cause any disease. So the humidity of cabin will reduce because we will no longer have the recirculation. But the good thing is that the smoke will not coming back to the cabin or cockpit. So system will shut down the recirculation fan, and also the system will speed up the bay fans, because provided that we have smoke inside the bay, we need to cause a negative pressure inside the bay to avoid the smoke to ingress back through the air conditioning return area, okay? And additionally, we have some aircraft flight manuals instructions for the pilot how to proceed. So for example, if I have a smoke in a given bay and the detector detects smokes in that bay, the indication in the cockpit will show the pilot that there are smoke in that particular bay. So the pilot will read the manual of the aircraft, and the manual of the aircraft will set something, shut down the DC bus or shut down a specific bus that fits that particular bay. And after shut down that electric bus, probably the smoke will disappear. And then the aircraft flight manual will explain which would be the action for the pilot to do. For example, the flight manual can ask pilots to land as soon as possible or land as soon as practicable, okay? And we have also the smoke evacuation procedure in case the smoke ingress inside the habitable zone. There will be a specific procedure to evacuate smoke. in the aircraft, normally the procedure is to dump the aircraft, to shut down the pressurization, and perform a emergent descent to 10,000 feet to ventilate aircraft with hum air. Okay. So here is the same pictures. So, but this time, what's gonna happen? Okay. So here we will have a smoke detector here. You can see the smoke detector is in the outlet ducting. And provided that we have a smoke signal here, the ECS controller will send a warning signal to the pilot, and then the ECS controller will increase the speed of this fan, or will open this valve to throw the smoke outboard the aircraft. Okay. Well, which is the future of ECS? I have told you all this presentation about the bleed and pneumatic as a energy source for the ECS, but the truth is that people would like to change to something less that provide less hazard for the aircraft than bleed, because bleed basically is a hot air, and it's dangerous in case of failure. And currently we have the more electric aircraft concept. Instead of bleeding, we are distributing energy in form of electrical energy. As you know from the thermodynamics, this is not so efficient than use the energy in its original state, because you transform thermal energy from engine to electrical energy to make the and after you have the electrical energy, you transform again to thermal energy to cool down electronics and to make the air conditioning. As you know from thermodynamics, the irreversibility of this process is higher than use the energy in its original state. So thermal energy to thermal energy, okay? But because of a trade-off systems with that use electrical energy are becoming more and more attractive to the designers. Why this is occurring? Because we need to distribute the bleed inside the aircraft after cool down this bleed. So we lose a loss of thermal energy in per cooler. This is the main argument. We have restrictions for temperature inside the aircraft because we pass the ducts through regions when we have flammable atmospheres. For example, near fuel tank, or near fuel lines, or near hydraulic lines. So because we lose a lot of thermal energy in per cooler, maybe it's better to use more electrical systems. Maybe it's better to distribute the energy in the form of electrical energy. Okay? And currently we have operating in the industry some systems, some more electrical systems. As you know, the Boeing 787, the Dreamliner, is the first aircraft to be totally more electric. So this aircraft uses a pack that is bleedless. It's not exactly bleedless because it's a regular pack. It's a normal pack that has a compressor in its inlet to produce its own bleed. Okay, so inside the pack we will have bleed, we have compressed air, we have heat exchangers, we have some loss of thermal energy. But other systems are using a lot of electrical energy. For example, pressurization systems 20 years ago used pneumatic lines. Currently, they are using electrical actuation. Pneumatic actuation in pressurization systems is no longer a rule. And because of that, pressurization systems are becoming more and more reliable. The outflow valves currently are all electric actuated. They are no longer pneumatically actuated. And in ventilation, we used to have pneumatic actuated valve, but currently it's becoming an old fashioned. The ventilation valves now are more electric, and they are more efficient because we no longer need that higher and longer pneumatic lines to feed all these ventilation valves. So I think I finished my presentation. I know a word in Lithuanian. It's ačiū. Ačiū is the same as thank you. Thank you.
Okay, thank you, Fabio, for very interesting presentation. So maybe our students have questions. Okay, I self have a few questions. First, very interesting for me personally about clearance of filters and air system, air conditioning system, because the filter is very effective and good in airplane, but who is responsible for cleaning inlet and pipe till filters?
Let me come back here.
Because we know that after filter air is clean, but before filter.
Before filter, just
Yes.
a second.
Inlets and cabin.
The filter is in the inlet of the recirculation system.
Mm-hmm.
So it's not supposed to find viruses or bacteria here.
Mm-hmm.
Of course, that the ducting a long time will not become clean. Some dust and some contaminants will stay over the ducting.
Mm-hmm.
The cleaning of the ducting is made in some particular check of the aircraft. So when you reach these maintenance checks, you remove all the interior and clean all this ducting system. This is specified in the manual of the aircraft. So, for example, let's say that we have a biohazard contaminant here.
Mm-hmm.
Say one person that has for example, COVID or SARS or MERS. The filter will keep the system cleaned.
Mm-hmm.
If this particular person release a virus or bacteria inside cockpit,
Mm-hmm.
will come back through the return area. The filter will avoid the reingress, the reingress of this virus or this bacteria into the system, and then this contaminant will go outside through outflow valve, or will stay here, you know, and will die a long time. So the return area of the aircraft is not a. We have lots of impurities that is found here in this area here.
Mm-hmm.
And this area is cleaned up in a aircraft check. So there are specific checks that the interior is removed, and there is a specific procedure for cleaning the ducting in the manuals of the aircraft. Okay, but during operation, this is the rule. We have the HEPA filter here, we have a check valve, we have the fan, and all this system of downstream HEPA for sure will not have contaminants that can infect people inside cabin or cockpit.
Mm-hmm.
This design normally in 20 years ago, when we don't have news of infection disease, HEPA filter was provided as an optional for the aircraft. So the operators will pay a little bit more for the manufacturer to have their aircrafts with HEPA filter. But after we have news of infection disease across the world, the authorities or even the operators start to require the manufacturer to provide the aircraft with HEPA filter. Before 2004, when we have the SARS, I don't know if you remember, but in between 2000, 2001, 2002, 2004, we start to having infectious disease, news of infection coming from Asia. And well, the operators start to become afraid with this infection disease. Then they request to the manufacturers what they should do about if the engineering has a suggestion. And in that particular moment, when we receive this request, we start to study what would be the solution. And then we concluded that this technology of filter is very good for infectious disease, for viruses and bacteria. If you may ask me, well, but the virus is lower than the particle size of HEPA filter. This would be your first question, I imagine. The virus is lower than particle size of HEPA filter. Okay, but the point is that the virus is only alive if it is inside a droplet of water or inside a particle of dust. So, provided that this filter is very efficient to these droplets, to this dust, it can be a good mitigation, a very good mitigation for virus infections, infectious disease. And also for bacteria is very, very efficient. And but HEPA filter is not good for volatiles. For example, vapors and some smokes, some level of particle of smokes. HEPA filter is not good for mainly for volatiles. But volatiles is not exactly a problem. If we detect the smoke, we can shut down the recirculation fan. Okay, so this can avoid these volatiles to ingress in cabin, because volatiles can be detected by a smoke detector. So if we have a failure in the base, we will shut down the recirculation fan. That's it.
Okay, thank you. So maybe we have questions from students. It's clear for students. Okay, I have another question, but maybe it's related to our future lectures about using 3D printed components in aircraft and systems. What do you think? It's growing these technologies and going forward, or not? From your experience,
which components?
Valves, inlets, and combustors, or
here?
Yes, okay, and here.
Well, the challenge for components is the reliability. So, for example, there are many tribology studies for check valves. Check valves, mainly for check valves installed in engine. Are you see this check valve, for example? Are you see the LP check valve? This check valve has a very, very big challenge involved in the wear of the valve. So this valve starts to present a lot of wear. So there is a lot of studies and studies to improve its reliability. So we have wear of the seats of the valve, we have wear of the pins, and there is a lot of studies and development on this valve. It's a mechanical component that works in a high frequency and in a hot environment. As you know, everything stays over the engine has problems with reliability, because engine vibrates a lot and works in a high temperature. If you see this picture here, you can see that you have a lot of electronics here, because this is the cold side of the engine, despite being over the compressor, because the compressor is a hot place, but you have a lot of ventilation here. So you have a lot of issues related with vibration, and you see that the electronics concentrate in this portion of the engine. But I would like to ask you if you see electronics here. You see, there is not electronics here. You know, you see mechanical actuation, this portion of the engine, because here we have the combustion chamber. This place is excessively hot, and the check valve is installed here. So there is a lot of vibration. So in this case, it is a mechanical component that demands a lot of tribology studies to improve. You see, it's a ridiculous component. It's a two-piece component, but there is a lot of challenge in developing materials that withstand vibration and impact and wear. Okay, so this is a challenge for this component. And I don't know if you will stop using bleeding in the next 10, 20 years. Okay. Okay. It also involves, we have a lot of challenge involving wear and vibration involves. It is a very, very engineered, it's a high-level engineered component. It's a lot of millions of dollars involving in developing this particular component. And just for you to know, only one single valve like this is not bigger than a laptop. It's worth more than a luxury car. For example, the price of this valve can reach a price of Mercedes-Benz MAG, you know? It's a very expensive, a lot of exotic materials. The seals inside this valve are made of special materials that are not able to pronunciate their names, you know? They are very complex. And there are lots of studies and development in these components. Precooler, well, the challenge of precooler is the reliability, okay? So there is a lot of issues involving in manufacturing process. Here they are mentioned Inconel, but there are lots of alloys. Several alloys of Inconel, several alloys of stainless steel and titanium. And this is a very, very engineered component. This it's a very expensive to development one heat exchanger. You see here, this heat exchanger is for Pratt & Whitney engine that equips the 777. This other precooler, it's for the General Electric engine, and the other precooler is for Rolls-Royce engine. So the three precoolers equip the same aircraft, the 777, but they are different. It's because they are tailor-made for the engine. So a lot of hours of engineering are used to design these components. And the design of these components involve CFD, computer fluid dynamics, because we have stratification issues in the inlet and outlet, involves a concentrated parameter simulation. We use sometimes softwares with distributed parameters like finite element modeling software to modulate the heat transfer. Sometimes MATLAB to simulate dynamically this. And for sure, we need to use finite element modeling to design the structure of this, because we have not only the stresses related to pressure, but we have stresses that comes from installation, stresses that comes from vibration. And the last thing that I would classify this is more exotic also, is because as you have higher flow for this component, you have vibration induced by flow. Could you imagine this? If you have higher flows, you have vibration induced by flow. So this phenomenon, you can only see this through a CFD analysis. Okay, it's very difficult, even for CFD analysis, it's very difficult to see. Sometimes we don't detect the vibration induced by flow in CFD, we detect it only in operation. So we need to come back to our design boards and design again. For example, these elements here induce vibration that can destroy themselves. Okay? Okay. So the process of development is well known. It's not a subject for a university, for example, but for vibration induced by flow, it seems a new subject for industry. I remember the first studies. Well, despite we have studies for vibration induced by flow in the beginning of 19th century, the simulation tools only arrived in the industry in the last 20 years, and we are not capable to detect vibration through the current software. CFD softwares are not easy to detect the vibration. If you use, for example, large eddy simulation, we can detect. But if you use other techniques, for example, depending on the turbulence model that you use to study the flow, the vibration is not easy to detect. Okay. Mm-hmm. So this is a challenge that the industry is demanding from the university. Better models for CFD, for example. Okay. And for percoolers, the material challenge is related to fatigue. Okay. Mainly for the welding joints. Normally, we detect failure in welding joints, and the knowledge generated for characterize welding joints in these alloys is still an issue for the industry. You solve this with safety factor. We put lots of safety factor in these components. Let me see if I have other forefront in the development here. Well, I would say you that sensors, there are lots of technology development in sensors. Currently, if you ask me which kind of sensor I would like to have in my airplane, I would say to you that I would like to have microprocessed pressure transducers or microprocessor temperature transducers. What I would like to have in my aircraft? A sensor that reads the temperature and sends me a digital signal. For example, a byte in a label saying the state of the temperature, and, the logics related to failure condition of the sensor. But you know, this is impossible because sometimes this these sensors work in a hot environment and it's not possible to have microprocessors inside this place. So this is one challenge for industry, to have intelligent components. In fact, the intelligence is an important thing today because we prefer today work with buses instead of analog lines. The analog lines are susceptible to interference, and this is not good for industry. For aircraft, it's a problem. The electromagnetic interference is a very big issue. So we prefer to have intelligent components connected to digital buses instead of analog double wire lines inside the aircraft. And I can go beyond, you know. We can use, for example, optical fibers communication, you know.
Yes.
Optical fibers communication, they are totally immune to EMI. And currently we have some brake systems using optical fiber for communication. But the optical fiber has a bigger problem, that is the vibration. They are not reliable under vibration environment. But the big thing about optical fiber is that they are immune to interference, electromagnetic interference. This is a very good thing, you know.
Okay. Okay, so thank you for your very detailed answers. And so if you don't have more questions from student side, I would like to thank
you very much.